we introduce EgoGen, a generative and scalable synthetic data generation approach, specifically tailored for egocentric perception tasks. At the heart of EgoGen is a novel egocentric perception-driven motion synthesis model. Our key idea is to enable virtual humans to perceive their environment, thereby closing the loop on the interdependence between egocentric synthetic image data and human motion synthesis. To avoid expensive depth rendering and stabilize the reinforcement learning training, we propose to use compact egocentric sensing as a depth proxy. The body pose and shape are simplified using body markers, and the body marker location and direction to the target are encoded with GRU. Egocentric sensing is encoded with GRU to capture temporal information. The distance to the target and remaining time are encoded using positional encoding. We use the PPO algorithm to optimize a stochastic policy. The actor and critic networks are parametrized by MLPs. Given an arbitrarily synthesized motion sequence produced by our generative human motion model, we outfit virtual humans in diverse 3D textured clothing by performing automated clothing dynamics simulation with a state-of-the-art neural network. The embodied camera placement module supports simulating various head-mounted devices with different camera models and camera rigs. By positioning the camera on the head, we generate photorealistic egocentric synthetic data with rich and accurate ground truth annotations. EgoGen supports various cameras and camera rigs. We can render high-quality egocentric synthetic data with a rich set of ground truth annotations, including RGBD images, optical flow, surface normals, segmentation masks, object bounding boxes, world positions, and simulated motion blur for egocentric perception tasks. In the context of dynamic obstacles, obstacles move to block humans from reaching their goal. Despite augmenting previous works with dynamic path planning, they still encounter issues of penetration with dynamic box obstacles in the arm region. In contrast, we can synthesize collision-free motion sequences. Despite augmenting previous works with dynamic path planning, synthesizing realistic collision-free motion sequences for two people switching locations remain challenging. However, our method demonstrates the ability to generalize, even though it is only trained in static scenes. In a more challenging scenario involving the synthesis of four people switching locations, previous works struggle. In contrast, our method demonstrates generalizability and higher motion quality. Here we further compare previous works with our model in a crowded setting. The task is to synthesize the motion of 8 humans switching locations, with each individual reaching the target located across the circle's center. Previous works failed completely. Even though our model is only trained on static scenes, we can generalize to more complex tasks not encountered during training and exhibit higher motion quality. We further qualitatively compare the motion diversity of our method with Physics VAE. Physics VAE synthesizes completely symmetric crowd motion for stickmen only. The result is unrealistic when considering real human crowds. In contrast, our generative human motion model allows us to generate diverse crowd motions for diverse body shapes, incorporating variations in height and weight. This paves the way for diverse egocentric synthetic data generation. After comparing our motion model with previous works, we evaluate the effectiveness of our egocentric sensing. Using egocentric sensing as a depth proxy enhances the ability to see farther and explore more effectively. We substitute our egocentric sensing with a local map introduced in demos and adopt their encoding method. In a test scenario where the virtual human is in front of a long wall, relying solely on local information can trap the agent in local optima. In contrast, egocentric sensing enables the agent to walk across the long wall. EgoGen enables virtual humans to explore large-scale scenes, generate dense egocentric views, and build more complete structure from motion maps. EgoGen shows potential for building mapping and localization data sets for AR and digital twin scenes and enhances privacy preservation. We test the recent Human Mesh Recovery Model Pro HMR with depth images as input on a real-world dataset, EgoBody Test Set. Here the mesh color denotes the vertex error between the predicted body and the ground truth. Compared with a model trained from scratch on EgoBody training set, the model pre-trained with our generated synthetic depth data achieves significantly improved performance. Furthermore, we extend the assessment to Pro HMR with RGB images as input on the EgoBody test set. In contrast to the model trained from scratch on the EgoBody training set, the model pre-trained with our synthetic RGB data demonstrates improved performance.